morning, students. Welcome to the lecture number 30, Welding Defects, Causes and Remedies to get a defect-free welding. So the objective of this class is to understand the welding defects, causes and its remedies. So you will come across the terminologies like welding defects as surface defects and subsurface defect and NDT in this presentation. So what is defect? There is a similar terminology also you can come across, that is called discontinuity. Defect, if I say it is a defect, normally defect is a rejectable flow which is inside any material. It can be a flow or flows that by nature or accumulated effect render a part or product unable to meet minimum applicable acceptance standards or specifications. So that is called as defect. Discontinuity and interruption of the typical structure of a material, such as lack of homogeneity in its mechanical, metallurgical or physical characteristics. A discontinuity is not necessarily a defect. That is, normally we can call it as discontinuity in the welding. And all the discontinuities are not rejectable flows. Some are acceptable in nature. So rather than calling it as a defect, the ideal or the appropriate terminology to call it will be discontinuity. So we will see one by one of these discontinuities. So the first one or the major types will be misalignment, undercut, underfill, concavity or convexity, excessive reinforcement, improper reinforcement, overlap, burn through, incomplete or insufficient penetration, incomplete fusion, surface irregularities such as overlap, arc strikes, inclusions, can be slag inclusions, can be wagon tracks, can be tungsten. We can have spatter, arc craters and cracks. Cracks, many types of cracks are available: longitudinal, transverse, crater, throat, toe, root, underbead and heat affected zone, hot, cold or delay. It's not over. We will have base metal discontinuities such as lamellar tearing, laminations and delaminations, laps and seams. We will have porosity. Porosity can be again uniformly scattered, cluster, linear, piping, and also the heat affected zone microstructure alteration and base plate laminations, size or dimensions. These all discontinuities are commonly visible in the weld if you have not properly welded the material joints together. All these discontinuities will need not to be rejected as defect. Some to certain levels, some to certain levels will be acceptable. So mostly the acceptability will lie on the condition that where basically that material or that product is going to use. So depends on its usage, certain flows or certain discontinuities, we can say that they are defects. Either they need to get or majorly they need to get rejected. Or if a discontinuity is seen in a weld, you have to repair the weld. So if we talk to any industrial people, they will say that the repair cost is 10 times higher. Repair cost is 10 times higher than that of the production cost. So by any chance, if we can able to remove these discontinuities, to get a defect free weld, then That will be the aim of every welding industry. Certain defects, say for example, like cold or delayed cracks, or you can see something like this these kinds of base metal discontinuities. So these all may cause sometimes defects or discontinuities in the weld. So you have to properly take care of your material, you have to properly take care of your weld parameters, you have to properly take care of your weld environment. Okay, these all things normally, if these all things are perfect, then normally the chance of defects can be minimized. So we will see one by one little in detail. So what is misalignment? So as is shown over here, this is a groove joint. These are groove plates. So initially when you try to weld it, you can see one plate is kept at a certain distance higher, and in this condition you have put the tack welding. Now when you are going for the root and subsequent filling and capping weld, this misalignment will continues in the weld. So as a result, your total shape and dimensions of the joint will vary. That is, the plates are not aligned properly. As a result, whatever the defect is occurring, that is called misalignment. So amount a joint is out of alignment at the root. So bottom part of the weld is called root. So if the roots are not aligned properly, and hence as a result, the variation, so the different thickness or transition thickness, so all these reasons the misalignment will come. So you have to ensure that the properly you have placed the plates and you have performed the welding. That is, both the roots lie on the same surface before you carry out the weld. So once it is happened, you have to go for repair, you have to go for grinding. Okay, so if it is sometimes ID, that is the inside diameter of a tube, if it has got a misalignment, so it is not so easy to machine these criteria. So you have to be very careful to avoid these kinds of misalignment or fit up issues in the case of joints. So normally plate you have to keep in its position and you have to perform the tack welding. So tack welding, when you are performing, you have to ensure that both the roots are matching each other. So you can see over here, this is the one plate, this is the thickness of one plate, and this is another thickness of one plate. You can see this goes the high low condition has occurred. So this is a misalignment. As a result, the topography of the weld also changed, the topography of heat affected zone also changed. You can see the root shape, the root concavity, convexity, all these things are going to change in the case if there is a misalignment exists in the case of welding. So when you are performing the fit up, the proper fit up, you have to ensure both the plates will lie on the same surface. So misalignment has to be avoided. Now what happens is that if I want to avoid it on this area properly, on this plate I have to machine. So this side the material thickness is going to reduce. So that is the remedy only here right now. So depends on the application. If you reduce the thickness on one side of the plate alone, so slowly you can see the defects or any other kinds of cracks or any other defects, bending or sometimes failure will take place on this side. So proper fit up you have to take care in the case of welding. So the next defect, that is called undercut. So you can see this is the case of a fillet weld. So in the case of a fillet weld, so weld has happened on this edge, but you can see there is a gap on this side where the weld has not happened. So this is called the undercut. So this is called as the undercut. So a groove cut at the toe of the weld and left unfilled. So that is called as the undercut. So causes is high amperage, electrode angle, long arc length or rest. So these are some kind of issues which normally undercut will occur. So you can see some here high amperage, electrode angle, long arc length, these all are process parameter. Rest, that is there on the environmental condition. This is where I told you the environmental issues comes into the picture. So prevention, set machine on scrap metal, clean metal before welding. That is, whatever you are going to weld, check the amperage, check electrode angle, check long arc length, etc. on a trial or on a scrap piece, and ensure that no undercut occurs. And also you have to, once you the groove or whatever you are making, you have to ensure that these surfaces are properly cleaned with the help of some kind of we can even say that there's a mechanical cleaning processes are available. So some kind of mechanical or chemical cleaning processes you have performed on these areas to ensure that no grease, no hydrocarbon surface is present on the weldment area, which may cause you further defects. So you have to check the parameters and you have to properly clean the weld to ensure that no undercut is happening on the weld. So undercut will have a allowable limit. So different codes and standards vary greatly in the allowable amount. So based on the IWS or based on the AWS, so they will provide you that for a particular application or for a particular boiler application, there are ASME codes are available. For a particular coded applications, this is the allowable limit. So accordingly, so specifically whatever is mentioned based on the codes, whatever the industry is following, accordingly you have to limit these kinds of undercut values. So we can see over here, so this is the area where the undercut has happened, and you can see over here in this areas it has not properly fitted up. Okay, you can see over here this edges, so the weld has not, you can see over here the weld has penetrated to the base metal, whereas on these sides the weld has not gone to that areas. You can see here also. So this is what is called as the undercut, where a certain edge of a weld material is not joined properly. So that is called as the undercut in the case of welding process. So the next one is called insufficient fill or underfill. So you can see this is a double V groove. So one V groove over here and the next V groove is shown over here. So this is basically a double V groove joint, where you can see this is the area where the welded zone, okay, this is the welded zone area. Adjacent to it you can see a differently colored area is there, that is called as your heat affected zone, and these are the areas where your base metal is present. So here you will get a different microstructure, here a different microstructure will be obtained, here and another microstructure will be obtained. Anyhow, I am not going to the microstructure, it is insufficient fill or underfill. So when I did this groove joint, you can see here this is the welded zone from the top side, this is the welded zone from the bottom side. Here you can see in this area, okay, in this area it is only remains as an heat affected zone, but none of the weld either from the top or from the bottom has not penetrated into this area, and as a result they are still kept as a condition of insufficient fill or underfill. So this area is not filled properly. So that is called as insufficient fill or underfill condition. So improper welding techniques are the causes, or because of the insufficient welding techniques only the insufficient fill or underfill is happening. So apply proper welding techniques for the weld, basically type and position, use stripper beads before the cover pass. So repair, simply weld to fill, may require preparation by grinding. Okay, since this is already welded on the top, this is already welded on the bottom, again if you want a metal to be deposited, these areas you have to again cut so that this area will get penetrated. So again it is a rework. This is what I told you, repair or rework cost is 10 times higher than that of making a real-time welded job. So these kinds of flows you have to be avoided in the welt. So here also you can see this is again insufficient fill on the root side. Okay, so you can see on the root side the well has not filled. You can see over here. Okay, these all areas were unfilled from the root side. That is the top, or that is the bottom part of your plate. So that is called as a root. So root has not properly filled. So improper root penetration. That's the way also it can be also called. So now if you are keeping the plates with excess root gap, okay, excess root gaps if you are if you kept on the plate, or the joint configuration is not, or the groove configuration is not good enough, then the insufficient fill on the root side will happen. So typically improper joint preparation or excessive weld pool heat, that is also a reason. That is, excessive weld pool heat will also causes the material not to get fused and adhered to here. Instead of that, they will get melted and vaporized off. Okay, due to the excessive heat, the material on this edges or on this sides may get melted and vaporized off. So the joining is not taking place. Either the gap is high, or the excess heat causes these kinds of defect in the case of welding. So how to prevent it? So that we can see. So some liquids like water or molten steel try to cover as much surface area of whatever they are in contact with as possible. So welding a root pass too wide can also cause the bead to sag overhead position. So you can see. Okay, so this is how it has to be required. So if you keep it too wide like this, what happened? The same drop, so it tried to sag to both the sides. As a result, what happens is that you can see the shape will go like this. So you can see over here, these areas will not get properly fused or joined. Okay, the same thing will happen here. The material, here you can see the material thickness is very minimum. So if you are providing it with excessive heat, what happens is that these tip areas may get melted off. As a result also, the proper joining will not takes place. So you have to ensure proper root gap, that is exact root gap you have to provide. The minimum root gap or over root gap will create a defect, a root defect normally in the case of weld, and you have to select proper amperage in the case of welding, otherwise it will end up with a defective welding process. Yeah, so if a defect has occurred, then root you have to again cut, you have to grind it. Okay, so and then you have to perform the welding. So open the groove angle, be carefully to leave the proper root face dimension. Okay, feather the start and stop to blend smoothly into and out of the existing weld. Okay, so you can see over here how to cut it. So you can see, so initially this is the way which you have to cut it. Then yeah, so cutting that portion, yeah, you make it little more wider. So now your groove dimensions has obtained. Now in this groove again you have to fill to ensure that proper root concavity in the material and proper face concavity or convexity in the material is being obtained. Yeah, so you have to do the weld, then the next filling pass, next filling or capping pass. Okay, so this is, you can see this is multi-pass welding. So the bottom pass where the root is joining, okay, that is called as a root pass. The subsequent passes are called as filling passes, and the final pass on which the top bead profile you are obtaining, that is called filling pass. So root pass normally you have to perform in an optimal speed. Okay, and cap filling, the final pass also will be done on an optimal speed. The intermediate passes, they will go in a little faster manner. and every welding need not to go on these stages. It depends on your plate thickness, it depends on the groove configuration. Okay, anyhow, your groove configuration will depend on your plate thickness. So more the plate thickness, more the pass is required to fill the cavity. So you have to take care that into account when you are performing the welding. So this is how the defect can be avoided. Okay, if a root defect has occurred, this is how the stages in which you can perform the welding. That reworking of the welding stages shown over here. So already it is welded over here like this, like this. Now you have regrinded it, you have cut it over here, then you regrinded in its groove shape, again you are welding. This is why I told you the cost of a repair weld is 10 times higher than that of the normal welding cost. So the next term that comes in the case of welding, that is concavity. So you can see the profile of the weld in the case of a fillet weld. Okay, so how sag it is, so that's the way the convexity or concavity is defined. So this is a profile, so this profile is called concavity. So concavity or convexity of a fillet weld which exceeds specified allowable limits. Okay, so this has to come like this. So if it goes, if it exceeds, you can see, so this is the limit. So in this limit it has to complete the weld like this, as a profile like this. Instead of that, it is extended from this point to this point and from this point to this point in the other plate by an amount. So that is defined as the concavity in the case of fillet joint. So normally amperage and travel speed. Okay, so low travel speed or high currents normally will cause this kind of concavity defect in the case of welding. So proper parameter and proper technique you have to use to ensure you are getting a proper weld with proper concavity. The same is the case convexity. Okay, the weld has to end in this profile in a groove. So weld has to end in this profile, but you can see it has exceeded by a distance in both the sides, but the shape is only changing. That is called convexity. Okay, so that is called convexity. So convexity, we can say that rather than showing it on the fillet weld, it may get in this, it may get in the case of groove welding also. So you can see the excess concavity is shown over here. Okay, the excess concavity in the case of a groove weld, it is shown over here also. So both the sides on the plate, the weld has, so this is one view and this is the top view. This is the top view of the weld and this is the cut sectional view of the weld, where you can see on the cut section of the weld. Okay, so it has gone, the bead has gone to a wider angle, so that is called as the concavity. So root concavity, that is on the bottom side. So bottom side also excessively it has gone, so that is the root concavity. Okay, this is, I told you, if I say on the top surface, this comes as the bead concavity. So this is the bottom one, you can see there is excess, it is concave. So there is another way also, this will be also expressed, we call it as excess reinforcement, excess root reinforcement. That is basically in the case of welding, you are melting a material and you are depositing it. So melting a material, you are consuming the current, that is electric power is being consumed. And if you are providing excess current, what happens is, if you are providing excess amount of energy, that is when the excess reinforcement is taking place, excess amount of energy is used. Okay, when excess amount of energy is used, the melting efficiency or your joint efficiency, or what I can say, yeah, the melting efficiency is getting reduced. That is, this material can be used elsewhere in your joint, where by making a higher strengthen on this area is not at all needed or it is not at all recommended in your design. So this root concavity all will lead to the condition that the excess root reinforcement is taking place, which is not at all a desirable one. You have to avoid it. Yeah, you can see this is a reinforcement. So you can see there is root reinforcement as well as face reinforcement. So excess reinforcement is not required in the case of welding, only recommended reinforcement is required. Excess reinforcement normally creates an excess heat affected zone, and normally whenever or wherever you are seeing, where you are observing a failure in a welded joint, by if 80 percentage the weld defect will happen in this heat affected zone. It will not affect, it will not have in the welded zone, rather than it will affect on the heat affected zone. So the area of the heat affected zone, if you are able to minimize as minimum as possible, the chance of getting failure is also minimum. So if you want to remove that condition, only optimum heat for a lesser amount of time is on, you have to provide on the welding plate. So excess reinforcement either in face or in root is not required. So that is the way in which concavity, convexity can also be you can able to substantiate. So the reinforcement can be excessive, it can be insufficient, or it can be improper contour also. So excessive, insufficient also is not advisable, and improper contours are also not advisable. So you can see over here, this is excessive reinforcement. As a result, you can see the bead width is much higher. The width of the bead is much higher. You can see this is the excess reinforcement on the face, and this is the excess reinforcement on your root. You can see the deposited area of the weld metal in the top view. And insufficient reinforcement is that, so specifically defined by the standard, typically underfill may be up to 5% of metal thickness, not exceed to 1/32 inch, as long as the thickness is made up in the opposite reinforcement. So not applied to fillet welds. So that is proper reinforcement you have to obtain on the weld. Excess and insufficient reinforcement if you are providing, rather than the material joining in HAZ zone, that is a heat affected zone, the material will definitely fail in the welded zone itself. So cause on root reinforcement, too little filler material will cause thinning on the filler metal. Okay, so the prevention: use proper welding techniques, use backing or consumable inserts, use back weld or backings to support. So these are the ways you can ensure that proper reinforcement is taking place on the weld. So I have seen the application of backing plate in the manufacturing of pressure vessel. Okay, so there the backing plate is used and welding. So that is done to ensure that proper root reinforcement is taking place in the welding. You can see this is the third one, the improper weld contour. So improper weld contours are normally happens because of the poor welding techniques. So excessive reinforcement may also increase or may also create this welding improper weld contour. So when a weld exhibits less than 135-degree transition angle at the weld toe, we call it as improper weld contour. So the exact weld contour on the top is defined as it should have minimum of 135-degree angle. Lesser than that, you can see it will come as more flat. Okay, so more steep is also more steep, but height is also limited. So the weld contour also have a limitation. So when you are welding it, you have to ensure the proper welding techniques, so that the angle, the transition angle at the weld toe should be less than 135 degree. So a weave or whip motion can often eliminate the problem. Okay, so the weld face must be feathered into the base plate. So that's the way the repair welding you have to perform. Next is overlap. So when the face of the weld extends beyond the toe of the weld, so that is called as overlap. Causes due to the improper welding technique, typically electrode angles and travel speed. So overlap is a contour problem. Proper welding technique will prevent this problem. Okay, so you can see over here. So this is the limitation. This is overlapped by a certain distance. You can see over here. So this is the recommended one, but here and all you can see this is overlapped into the base metal. So this is only the desired. So whatever the metal you are pouring over here, that is actually does not have any use. So that's basically a waste you have to remove or you have to eliminate it. So overlap, due to this overlap, now you can see here the weld angle. Okay, the previously told the angles. So the angle dimensions will not met in this case. So that has to be taken care. So overlap is measured with a square edge such as 6-inch rule. No amount of overlap is typically allowed. Okay, that is basically the wastage of your melted material. So the next defect normally seen in the normally you can see in the weld is burn through. So burn through is nothing but instead of making as a joint there a hole is being produced in the weld. So that is called burn through. So when an undesirable open hole has been completely melted through the base metal, that is called as the burn through. The hole may or may not be left open. Okay, so excessive heat input is the reason of the burn through. Okay, so that is instead of welding, there basically the cutting is taking place. So a same electrode, the same SMAW electrode, not SMAW, same any welding electrode, if you increase the current, okay, you can use it for cutting. So as and when sir has told about the gas welding process, if you are increasing the heat, okay, instead of welding the gas, cutting is used. Same way, by increasing excessive current, normally instead of welding the same electrode can be used for cutting purpose also. So that is a burn through. So burn through is a definitely a rejectable or a repairable flow. It is not an acceptable one, whatever may be the weld or wherever the application is. So the next is incomplete or insufficient penetration. So incomplete or insufficient penetration when the weld metal does not extend to the required depth into the joint root. So that is called as incomplete or insufficient penetration. So causes low amperage, low preheat, tight root opening, fast travel speed and short arc length. These are the reasons for incomplete or insufficient penetration. So you have to use the correct factors to ensure that the incomplete or insufficient penetration doesn't happen in the case of welding. So same thing I have told you the fusion with respect to the fusion. Okay, so same is the case. So here no penetration, no proper penetration is taking place. This is the case of root of a well. Here no proper root gap you have not provided, or when I kept this plate it has gone into a tapered condition. Okay, the tack welding creates a groove in a tapered condition. As a result, you can see here this is excessive root reinforcement followed by an area where no root reinforcement does not takes place at all. That is, the fit up between these two plates are not good enough. So you have to carefully choose or keep the plates in order to ensure the proper penetration is taking place. You don't need excess, you don't need no, you need to have a sufficient condition. So incomplete fusion is also similar, where the weld metal does not form a cohesive bond with the base metal. So that is called as the incomplete fusion. So that can happen in the case of sidewalls. Okay, between layer to layer also that can happen. Everywhere the chance of incomplete fusion is there. So low amperage, steep electrode angles, fast travel speed, short R gap, lack of preheat, electrode too small, unclean base metal, arc of seam. So these are the causes for incomplete fusion. So you can see over here, this is a case here. In this case, you can see this is also a multi-pass well. Initially, you can see this is the root pass, the next pass, the next, the next. You can see all this wherever it is showing in a different color, that corresponds to different passes of the well. Where you can see over here on these sides, okay, on these sides, the weld has not fused with your base metal. So this is basically the lack of sidewall fusion. Now between these layers also sometimes the defect may occur. Okay, that is the fusion doesn't happen between the layers, or inter layers also the fusion may sometimes may not happen. So the lack of fusion can happen between the sidewalls, between each layers are also possible. Okay, and this figure you can also see over here, this is another defect which we have discussed already, is also visible in this figure. Okay, so you can think of what was it. I am not going to discuss it. So next one is arc strike. So arc strike is a localized coalescence outside the weld zone. That is, you can see this is the elsewhere, these droplets of the material has fallen elsewhere in the plate, not in the joint. That is, you when you are welding it, you are daydreaming it. As a result, it is not going into the joint, it has fallen elsewhere. That is called as a arc strike. So causes us carelessness. So if it is a difficult area, what you have to do is that fire blankets you have to use to ensure that the arc strikes will not happen elsewhere in the welded zone. Other than the welded zone areas, nowhere the arc strike is going to happen. So if found, they must be removed and repaired using a qualified repair procedure and inspected as any other weld. Okay, so that's arc strike. Now next is weld spatter. So you can see here, this is your weld zone area, and you are expected the metal, the droplet, whatever is detaching from your tip of your electrode, that you are expecting to fall in this weld molten weld puddle. But what happens is that the droplet has fallen elsewhere on your surface of your plate. Okay, this is not because of your carelessness, because of certain other factors. If it has fallen elsewhere on your plate on both the sides, they are called as spatter. So causes are high arc power, magnetic arc blow, incorrect settings for GMAW process, and damp electrode. So these are the reasons for weld spatter. So spatter also you can see here, this is you are basically wasting your energy. So these all metals you are expected to be on the weld zone, instead of that they falls elsewhere on the plate. So you finally, when the spatter has happened, you have to regrind on this the entire surface to remove the spatter off. Okay, so that again is a reworking process. So the next one is called slag inclusion. So that normally will happen in the case of SMAW process or multi-pass welding processes. So what happens is that the slag, as you know, that is the impurities which are present inside the material. So flux will react with the atmosphere as well as with the base metals to ensure that whatever the impurity is present over there, that will float on the surface of your material. So once the welding is over, normally you will chip the top surface so that the slag will be moved away from the plate. But without chipping, if you try to again weld on the surface, what happens? The slag will be now inside your weld. Okay, so this slag inclusions normally will create a brittle area or a brittle surface inside your weld joint. So when a brittle area is present inside your well joint, normally what happens is that will be the nucleating agents for your further cracks or further any other defects to be propagate from the well. That will be your generating area. So these kinds of slags may sometimes will get entrapped into your well. So you have to ensure that the proper cleaning, if you are going for a multi-pass well, proper cleaning of the surface after a pass has been completed. Otherwise the slags will get deposited and you will get a brittle welded joint. So the cause, again you can see it is low amperage, improper technique, trying to weld in an area that is too tight. So slow travel in vertical down. So these all are the cause, these are the reasons why the slag inclusions will takes place. So you have to take the opposites of it to ensure that no slag inclusion is taking place in the case of welding process. Next inclusion, that is called tungsten inclusion. So tungsten inclusion normally you can observe in the case of a welded component which is done with the help of GTAW process. So GTAW process only will use a non-consumable tungsten electrode. So what happens is that as a prolonged usage, okay, the tungsten material which is there on your tip of your electrode may get broken and deposited into your weld joint. So that is called as the tungsten inclusion. So you have to ensure that the tungsten electrode will not get melted and will not get deposited into your joint. So the reasons is that electrode is too small, amperage too high, AC balance on. Okay, these all are some kind of reasons for the tungsten inclusion. So by proper setting on your machine, you can avoid the tungsten inclusion into your material. Now we will see the cracks. So the cracks, again on the well, there are types of cracks are available. You can see we will have longitudinal, we will have transverse, we will have crater, we will have throat, toe, root, underbead and heat affected zone, hot, cold or delayed one. We will see some of it. So longitudinal cracks. So you can see a crack running in the direction of a weld axis may be found in the weld or base metal. So that is called as a longitudinal crack. So causes preheat or fast cooling problem, also caused by shrinkage stress in high constrained area. So these are the areas for longitudinal crack. So a crack running in the direction of the weld axis may be found in the weld or in base metal. So everywhere the crack may present, that is called as the longitudinal crack. So the next crack, that is called transverse crack, a crack running into or inside a well transverse to the weld direction. So causes weld metal hardness problem. So a crack running into or inside a well transverse to the weld axis direction. So that is called transverse crack. And the reason is hardness of the material is not uniform. So this is a material dependent issue. Next is called crater crack. A crack generally in the shape of X which is found in a crater. Crater cracks are hot cracks. Okay. Cause the center of the well pool becomes solid before the outside of a well pool, pulling the center apart during cooling. That is, improper cooling is the reason for getting the crater crack. So crater crack also needs to be avoided. Proper cooling methodology you have to advise in the welding, or you have to change the electrode in such a way that the center area of the well will not cool faster than the outside areas. Next is throat crack, a longitudinal crack located in the weld throat area, that is called the throat crack. Okay. Next one is toe crack. So a crack present in the toe area of the weld. So that is called the toe crack. Okay, a crack in the base metal beginning at the toe of the well. So transverse shrinkage stresses indicates a heat affected zone brittleness problem. So toe cracks indicates the HAZ brittleness problem. So you have to preheat the surface, preheat the area wherever the weld is going to takes place to ensure or to prevent the toe cracks to be get happen in the case of welding. So these are the toe cracks shown over here. So next is called root crack. So a crack in the weld at the weld root. So that is called as the root crack. Again, transverse shrinkage stresses are the reasons for the root crack. So it is the same as that of the throat crack. You have to preheat the area to ensure that no root crack is taking place. Okay, so you can see over here. So you have to ensure preheat of the material to ensure that the uniform heat deployment will be there on this area, so that these kinds of cracks, effect of cracks can be minimized. Next is underbead crack. So a crack in the unmelted parent metal of the heat affected zone, that is called as underbead crack. Also is called as hydrogen embrittlement. Okay, so use of low high electrodes and or preheat, you can able to avoid it. So cracking, so you can see this is a high hydrogen concentration. So when the liquid metal, when it is getting solidified, hydrogen will be present over there. When it gets solidified, hydrogen will escape from that area, will create a pore on that area that normally will continue in the form of a crack. So hydrogen embrittlement, that is normally called as the underbead crack. Okay, so you can see the tensile stresses, the susceptible microstructure and hydrogen concentration. If all the three are present, you can see cracking will take place at room temperature itself, that is the underbead crack. So a hard crack in the weld that occurs during solidification. Microstresses from the weld metal shrinkage, pulling apart the weld metal as it cools from liquid to solid temperature. We have discussed earlier, so I am not going details into it. So next is cold cracking or weld metal hydrogen crack. So here what happens is that initially you have did a good weld, but when the weld solidifies or even after some days, you can see a crack is present on the weld surface. That is a crack that occurs after the metal has completely solidified. Okay, so that is called as a cold crack or weld metal hydrogen crack. So cause shrinkage, high restrained welds, discontinuities. So these all are the reasons of the cold crack. Need not to be even cold crack also. Sometimes you can see after post welding the material, if you the material may get warped also. That is a 90-degree blade. After welding, it may change the angle either to this side or this side. Depends on your post welding issues. So if a crack is obtained after your post welding, that is called as the cold crack or weld metal hydrogen crack. Now these all are some kind of defects normally happen inside your weld zone or on the heat affected zone. Now we will see some of the base metal discontinuity. So base metal discontinuity, the first one is called lamellar tearing. So lamellar tearing is happening in the area, okay, is happening in the area on the base metal. It is not seen on the welded zone, it is not seen on the heat affected zone, but wherever the HAZ is joining with the base metal area, there actually the lamellar tearing is taking place. So you can see over here. So normally this is happening because when you are making a grooving over here, if any layer or if you have not properly finished it, because of that reasons, okay, this kinds of lamellar tearing will takes place. So you can see the laminations and delaminations, that is also a base metal discontinuity. Okay, so this is one, lamellar tearing is one, where you can see the tearing is taking place in the base metal area. Laminations and delaminations are the second one. It is formed during the milling processes. So this is, you can see over here, I did a groove over here and I did a well. You can see lamination has taken place here. Now if I want to avoid this, I just change the joint configuration like this. So when I did it like that, I can ensure that these kinds of lamination effect can be minimized. So the third type of base metal discontinuity, that is lamps and seams. So a mill included discontinuity in which results from a lump of a metal being squeezed over into the surface of the material. So if beyond acceptable limit, must be removed and repaired or discarded. Okay, so these all are some kind of base metal discontinuities normally happen in the case of welding. So the next one, or the important defect happens in the welding, that is called porosity. So porosity is also, I cannot say it is a defect, it is a discontinuity. Certain levels of porosities are acceptable, depends on your application. So porosity can be of single pore, it can be uniformly scattered, it can be cluster, it can be linear, or it can be piping. So you can see on these areas there is no metal has been fallen, they are empty spaces normally called as the porosity in the case of weld joints. So single pore or individual pore, you can see at a certain distance apart only one kind of porosities are present, they are called as single pore or individual pore. So uniformly scattered porosity typically judged by diameter and proximity to a start or stop, often caused by low amperage or shorter gap or even an unshielded weld stud. So on the start or end of a weld, if you are observing a porosity, that is called uniformly scattered porosity. So cluster porosity typically viewed as a single large discontinuity. So you can see in between certain areas the defects are occurring. So they are called as a cluster porosity. Linear porosity, being linear, greatly affects the severity of this discontinuity. So throughout this weld area the porosity is going to happen, that is called as the linear porosity. Piping porosity generally has special allowable limits. So on the piping surfaces or on the piping areas. Another type is also shown over here, wormhole porosity. So again depends on the application, certain porosities are rejectable, certain porosities are acceptable, certain things you need to repair or rework. So another one defect normally in the weld, you can see it is unacceptable weld profile. So you can see of these kinds of various things, if a non-qualified welder is performing a weld, you can see these kinds of defects will occur. Unacceptable weld profiles. You can see now over here, these all things can be treated as your linear porosities. You can see over here. Okay, so these all are individual, this is single pores. Okay, so that's the way the porosity is. So unacceptable weld profiles will have plenty of weld defects accumulated in a single condition. So that is the unacceptable weld profiles. So if we see the weld, if we see the defects or on the weld, so certain defects are planar defects and certain defects are voluminar defects. So cracks, lamellar tears, lack of fusion, lack of penetration, etc., they can group under planar defects. Whereas porosity, slag inclusion, tungsten inclusion, etc., they are voluminar defects. So these all things will affect on a plane, either in x direction or in y direction or in xy direction. That is the planar defects. Voluminar defects, that will happen in x, y and z directions. Now if a defect is occurred on a weld, how do we able to identify there is a defect has occurred in the weld? So that is what is the purpose of testing of the weld joints. So if I say the testing of weld joints, testing is done basically under two broad classification. One is called destructive testing and the other is called non-destructive testing. So when you studied about the material science, you might have studied about the process called tensile testing or tensile testing, where the material is connected, material is designed on its specification, ASTM standards, and based on the ASTM standards you have connected it to a UTM, you have elongated it, and the material has moved from the elastic limit, it comes into the plastic limit, and finally the material breaks. So such kind of testing process, that is called destructive testing process, where the specimen you have made, specimen you have destructed, and you are finding or evaluating the characteristics of that particular specimen. So that is the destructive testing process. So normally in the case of a casted product or in the case of a welded product, the common testing procedure normally used to identify whether any surface defects are present or subsurface defects are present, they are called as they are use the process called non-destructive testing. So if it is a surface flow, you can visualize or you can determine with the help of visual inspection. Okay, the visual inspection is one of the common inspection process to see any surface defects are present on the material or not. You can go for magnetic particle inspection, you can go for fluorescent dye penetrant inspection to determine the surface flow. But if you have a lack of fusion, lack of interrun, lack of sidewall fusion, lack of penetration between, lack of penetrations, etc., by the any of these three above methods you will not be able to determine. Or a porosity, a shrinkage porosity is present in the case of a casting, then you have to go for the techniques like radiography, ultrasonic or eddy current testing to determine the internal flows which are present inside the material. So just an overview, I'll go through the various NDT process, just only an overview. I think that this is an elective subject that you may get taught in the coming semesters. So NDT, so this there is a website called ndt.org. The slides from here onwards, whatever I am showing you is just copied and pasted from the NDT website. I have not altered or I have not modified anything. Only whatever is required, only whatever minimum thing only I am showing here. More information you have to refer the ndt.org website. So what is NDT? So NDT is the use of non-invasive techniques to determine the integrity of a material, component or structure, or quantitatively measure some characteristics of an object. That is, inspect or measure without doing harm. That is called NDT. So you can see some kind of energy is penetrant into the material to study that there is no flow is present inside this object. Application of NDT, if I am talking, it doesn't limits to the areas of just like a casted product or just like a welded product, where plenty of other applications are there for NDT also. So some of the important or the methods of NDT so will be visual, you can see acoustics, liquid penetrant, eddy current, magnetic particle, ultrasonic, laser interferometry, microwave, etc., etc., etc. Okay, thermography, etc. So each one will have its own application in its own areas. Okay, so what are the some uses of NDT methods? So flow detection and evaluation, leak detection, location determination, dimensional measurements, structure and microstructure characterization, estimation of mechanical and physical properties, stress, strain and dynamic response measurement, material sorting and chemical composition determination. That is, you can see to here a wide variety of applications you can use NDT or NDE methods. Okay, non-destructive evaluation or non-destructive testing methods. That is not only used or not only limited to your casting and welding defect determination, plenty of other options are also available for NDE methods. So the six most common NDT methods, the basic one is visual, next is liquid penetrant, next is magnetic, next is ultrasonic, next is eddy current and next is X-ray. So you can see over here, this person is using, okay, this person is using some kind of tools, includes fibroscopes or borescopes or magnifying glasses and mirrors. So he is using some kind of magnifying device and he is visually inspecting a part. Okay, so with the help of naked eye or with the help of magnifying glasses, if in the case of welding or casting, if you are trying to determine a surface defect, okay, only a surface defect will be able to visualize with the help of visual inspection. So that is called as the visual inspection. So you can see over here, portable video inspection unit with zoom allows inspection of large tank and vessels, railroad tanks, cars, sewer lines, etc. So visually a person is inspecting a component with his eyes, that is called as the visual inspection. Okay. If it is a hazardous environment, you can use the robotic crawlers. Okay, in the tight areas such as air ducts, reactors or pipelines, you can use these kinds of robotic crawlers. But you are viewing on a screen with your naked eye and you are observing the surface. That is what is called as the visual inspection is. So any surface flows, okay, which are in the range of macroscopic condition, you can able to detect with the help of visual inspection. So a microscopic flow, you will not be a microscopic determinable flow, you will not be able to see with the help of this visual inspection. So in that case, for the surface defects, you have to go for liquid penetrant inspection. So in welding, this is in welding as well as in the case of casting also. So surface defects, a surface crack has been obtained. If a surface flow is there, this is one of the common, easiest and cheapest technique which you can able to use or employ on a welded area to see any surface defects are present or not. So a liquid with surface wetting characteristics is applied to the surface of a part and allowed to time to seep into the surface, breaking defects. So the excess liquid is removed from the surface of the part. A developer powder is applied to pull the trapped penetrant out of the defect and spread it on the surface where it can be seen. So then you can see to visual inspection on the final step in the process. The penetrant used is often loaded with a fluorescent dye and the inspection is done under UV light to increase test sensitivity. So visually you are not able to observe it, but a crack is present, that is in the range of microscopic order. So in that case, first what you have did is you have applied a liquid penetrant on the surface. You have allowed some time for the liquid penetrant to get penetrated into the crack. Then the surface of that wherever you have applied, the surface is completely cleaned off. but the liquid which is present inside the crack is not removed off, only the surface is clearly cleaned off. Now the next is the applying of developer. So the developer will allow us to see that where actually now the penetrant is, where actually the liquid penetrant is present. That area will be you can able to see with your eye right now that where actually the liquid is present. So these things, normally these developers or whatever the penetrant you are using, that is often loaded with a fluorescent dyes. So under light you can able to see that a crack is present over here. You can see over here, these are the areas where crack is present right now, but initially with the naked eye you are unable to observe it, or with the help of a magnifying lens also now you are unable to observe it. Now the surface layer, the microscopic surface defect, it is easily traceable with the help of a liquid penetrant inspection process. Next is magnetic particle inspection. So a part is magnetized. Finally, milled iron particles coated with a dye pigment are then applied to the specimen. These particles are attracted to a magnetic flux linkage fields and will cluster to form an indication directly over the discontinuity. This indication can be visually detected under proper lighting conditions. So you can see over here. Okay, so wherever the flows are there, that can able to easily determine. So magnetic field lines, if there is no discontinuity, it will move in a continuous fashion. Wherever a discontinuity is taking place, so that acts as your, so you can see this is your north and this is your south pole. So here again you can see a discontinuity will create your flux leakage. So this flux leakage will change the direction or orientation like this. So if you light those areas, that discontinuity you are able to obtain. So that is called as the magnetic particle inspection. Yeah, so you can see over here. So this is a case of a hook. Hook is having a defect. So the defect is easily determined with the help of the magnetic particle crack indication. Don't think that it is possible. Sometimes even in the case of dye penetrant test also, this is able to visualize. Again, in the case of a gear tooth, here a failure or here a crack is happening. So the surface defect you are able to determine with the help of magnetic particle crack indication test. Next is X-ray. You know the purpose of X-ray, how the X-rays are used or how the X-rays are working. Okay, so if you keep there is a subsurface defect has occurred. So a film radiography techniques normally you will employ. So now this is the defect. It is present inside your material, not on your surface. So you can observe that in the case of X-ray film, whatever is being developed. So this is the less exposure area. These are the more exposure areas. Okay, so the thickness of the material variation can be also determined. So a flow you can able to develop on a film. So that is called as the X-ray. So X-rays are harmful when you are playing with it. The area wherever you are using it, so that chamber, everything, you have to ensure that no leakage is taking place. So you can see the radiographic images. Okay, wherever the defect is observed, so that you can able to easily observe in the case of X-ray images. Not only in mechanical parts, even in PCBs also they are used to determine the flows inside to it. So the next is eddy current. Okay, so only thing is that the wherever you are testing it, it should be a conductive material. Okay, so eddy current will takes place. Yeah. So eddy current testing is particularly well suited for detecting surface cracks, but can be also used to make electrical conductivity and coating thickness measurements. Okay, here a small surface probe is scanned over the part surface in an attempt to detect crack. Okay, so next one is ultrasonic inspection, that is also normally seen in casting plants as well as in the welding areas. So that normally you can see high frequency sound waves are introduced in the material and they are reflected back from the surface flows. So here it has, there is no flow, so the sound wave had traveled the entire length and it has came back. Now here a discontinuity happens. As a reason of the discontinuity, the sound is traveling back in a shorter time. So that is being recorded. So the crack echo. So this is the initial pulse, whereas there is no defect is taking place. When it is encountering with a crack, you can see that the crack echo is minimized. That is the travel time for your sound wave is minimized. So as a comparison with this, you can able to see where actually the defect is happened and to what length the crack is present inside the material. So that is called as ultrasonic inspection pulse echo technique. Okay, so ultrasonic high resolution imaging can be also produced by plotting signal strength or time of flight using a computer controlled scanning system. So these all are, yeah, you can see. So grayscale image produced using the sound reflected from the point surface of the coin. Okay, so you can able to see where all basically the defects are being there on the surface. So these all are some kind of common NDT techniques which are used in the case of identifying the defects. So I just given you an overview about the weld defects, the reasons. So if you say the weld defects, improper weld settings, improper material handling, improper environmental issues, okay, and sometimes whatever the flows inside your material also may end up in the welding defect. And if a defect is occurred or not, you have to test it. Common testing procedure is NDT process. So if a defect has occurred, you have to see to it whether it is a repairable or an acceptable flow or not. If it is unacceptable, don't worry, you can continue as it is. Otherwise, you have to go for a repairable flow. So a repair welding normally will takes 10 to 20 times, okay, 10 to 20 times. The cost of repairable welding will be 10 to 20 times higher than that of a normal welding. Now think of a condition where I can make a weld without any defects. No NDT techniques is not required. No other processing is not required. But I have to control my weld process monitoring parameters at the same time of welding is taking place. Okay, that is when a weld is taking place, I am getting the feedback. Okay, I am getting the feedback on the welded area. So on a real time, I am able to see to that no flows are happening in my defect. Think of such a situation. That is what is called as online monitoring system. Not only to welding, it can be applied to any of your machining or manufacturing fields. Online monitoring systems, either in welding or in machining. Okay, so which again minimizes your production cost beyond to an extent. So these all are the developments happening in the manufacturing, moving from Industrial Revolution 1.0 to Industrial Revolution 4.0. Okay, so I am stopping here. We will continue further in the coming classes, higher classes. So I'll wind up here. Thank you. Any questions or anything to be discussed, we will discuss in the tomorrow's class. Thank you all.